Welcome to Brain Vision.
Okay, so the problem we're trying to solve is this. You have some current carrying rectangular loop of wire that's carrying some current that's 8.2 amperes in the counterclockwise direction. And and it's pivoted about this point on the z-axis. So along this line on the z-axis. And this exists in some external magnetic field that I'm just going to denote with a line, in some external magnetic field. Let me use a different color. In some external magnetic field that points along the y-axis, right? And I'll denote my magnetic field with a B. And this is suspended. That's you're this The magnetic field is causing the loop of wire to be pushed outwards, and you're asked how strong does this magnetic field have to be for this angle with the y-axis to eventually be 30 degrees. Okay, so that's the problem. Right, so whenever you see anything that involves turning about some axis, the first thing you should think of is angular momentum or torque. And I would suggest if you're not too fresh on that topic to go back and revise that, because that's essentially the concept that we're going to use here. And what our strategy is going to be to first find the torque. I'll denote with the tau. The torque due to gravity, the sub g, tau sub g is the torque due to gravity acting on this rectangular loop of wire, and equate it to the torque due to the magnetic field on the wire. Now remember, this is an external magnetic field. If you're thinking that there's a magnetic field because of the current, that's correct, but that's not the magnetic field that we want to use to find the torque on this piece of wire. That magnetic field will typically be very small, and for all intents and purposes, it's okay to ignore that magnetic field due to the current in the wire. So we're just concerned with this external magnetic field pointing in the y direction. So now let's find this quantity. First, let's find this guy, the torque due to gravity. The first thing you need to remember is that the torque always acts to the center of mass. And you can, for an arbitrary shape, if it's a more complicated shape, you have to use an equation to find the center of mass. But in this case, the center of mass for a rectangle is exactly the center of the object, exactly this point. So the torque is going to act through this point. And you must remember that the torque in general is just R cross F, where F is the force, right? So the torque due to gravity is just R cross the force due to gravity. And remember, R is the vector that connects the center of mass to the pivot. So it's this line. This guy, this line is R. Another way to write that, well, of course, the cross product, you can just write that as the magnitude of this vector R times the magnitude of the force due to gravity, just the magnitude of this force, times sine of theta, where theta is the angle between the force due to gravity and this vector R. So what is that angle? Let's try to figure that out. And I'll make a simpler diagram on one side, because this diagram is getting kind of cluttered. And so if I were to just draw a simpler diagram, this is this line. This is the y-axis essentially, and this is connected to the center of mass. That's what I'll call the center of mass. And this is my vector r, and this is my center of mass. And this angle is just this angle. It's just that angle. That's 30 degrees, right? And the force of gravity always acts downwards. So the force of gravity always acts downwards. This is f of g. And that's just mass times the acceleration due to gravity. That's just mg. That's just mg. So the torque, so if I plug this mg in for here, and note that the angle between r and fg, f sub g, is just 30 degrees, just this angle. This is the angle between this vector and this vector, because if I were to extend the vector r, then this angle is the same as this angle. This angle is the same as this angle. That's just geometry. So that means I can write the torque due to gravity as the vector r. The vector r, by the way, what is r? Well, r is from the center of this rectangle to this pivot. This side, if you read the question, this side, this left side and this right side, these are 8 centimeters. So that means this perpendicular distance to the pivot is just 4 centimeters. So that's 4 centimeters, which is 0.04 meters. 0.04 meters times the force due to gravity, that's mg. This m and this m are different. This m is in meters. Let me use a different color. Let me use a different color to denote that this is meters. This is not mass. Times sine of theta. Sine of theta. And we just established that theta is 30 degrees. That's the angle between the two vectors. Times sine of 30 degrees. So we're done with at least one part of the question. We're done with what we wanted to find on one side of this equation that we're trying to solve for. So now let's find the torque due to the magnetic field. Let's find the torque due to the magnetic field, tau sub b. And if you look back at the book, they in equation 27.23 gives a very neat formula for trying to compute the torque. It's just the current times the area times the external magnetic field times sine of phi. And phi is the angle between the normal to the loop and the magnetic field. So if I were to draw a simple diagram like I did before, then if this was my y-axis, and this was the vector r that we drew before, right, to the center of mass. This is the center of mass. This angle was 30 degrees. This angle was 30 degrees. Then the normal to the, now the loop points in this direction along the vector r, right? And so the normal to the loop is always, it's the vector that's perpendicular to the surface, it's perpendicular to the plane of the loop. That's this vector. That's this vector. We call this vector n hat. I think the book also calls it the vector A, the area vector, but that's just a name. So we'll call it the vector n hat. And the magnetic field points straight up. The magnetic field points straight up. Magnetic field points like this, in that direction. In that direction. And one thing that you want to keep in mind is that by definition, the normal makes this 90-degree angle with the r vector from before. And so this angle is 30 degrees. And this line, this red line, and this solid black line are parallel, which tells me that this angle is also 30 degrees. But that means, and this angle is 90 degrees between the normal and the vector r. That means that this angle between b and n hat, this angle must be what? Well, just 90 minus 30. 90 minus 30, which is 60 degrees. 60 degrees. And that's it. We're done with the hardest part of the problem. And now I can compute what tau sub b is, what the tau due to the magnetic field is. Well, that is the current. I know what that is. That's 8.2 amperes. That's given to me in the problem. Times the area, I can compute that because I know both the sides of the rectangle, 6 centimeters and 8 centimeters, times the magnetic field. That's my unknown. That's what I'm trying to solve for. Times sine of phi. And phi is this angle. It's the angle between the magnetic field and the normal to the loop. Normal to the loop. So that we just concluded is 60 degrees. So let me just put that in. So now I can just solve for b because everything else is completely determined. So as I said before, I want to equate the torque due to gravity to the torque due to the magnetic field. Let's write that out. Torque due to gravity to the torque due to the magnetic field. And so the torque due to gravity, that's what we just found earlier. That's what we just found here. That's what we just found here. That's R is 0.04 meters times G times M, the mass. And so there's actually one more step that we need to do, which is we need to find the mass. So what's given to us currently, I'll just do this on the side here. What's given to us is the mass per unit length. Mass per unit length. And that is 0.15 grams per centimeter. Grams per centimeter. Well, if I want to find the total mass, I just need to multiply this number with the total length of the object. Well, that's nothing but the perimeter. I'm just adding up all of the different sides of the rectangle. So that would be 0.15 times, well, the two sides which are 6 centimeters long, plus the two sides that are 8 centimeters long. 6 plus 6 plus 8 plus 8. That's 16 plus 12. That's 16 plus 12, which is 48. Sorry, 28. 16, 2 times 8 is 16, plus 6 times 12, which is 6 times 2, which is 12. 12 plus 16 is 28. And 28 times 0.15, and you should check this on your calculators, gives me 4.2 grams, 4.2 grams, 4.2 grams. And that's what I want to put in here. That's what I want to put in for M. 4.2 grams, or I should write it in proper units, which is 4.2 times 10 to the minus 3 times 10 to the minus 3 kilograms. And G is just the usual 9.8 meters per second squared. Meters per second squared. And this is, again, multiplied by sine of 30 from what we found earlier. Sine of 30. So this times sine of 30, right? That's tau of G, and I want to equate this to this guy, IAB sine theta. Well, sine 60. I is just the current that's given to me. That's 8.2 amperes. The area is just 6 times 8. So the area is 6 times 8, which is 48 centimeters squared. And again, I should use the right units. So in order to convert centimeter squared to meter squared, I divide by 100 twice, right? Once for 1 centimeter and then twice for the second centimeter. So I divide by 100 squared. In other words, this is just 48 times 10 to the minus 4 meter squared. And then I have the magnetic field, which is what I'm trying to solve for. That's the quantity I'm trying to solve for. Times sine of 60. This quantity, sine of 60 degrees. And the rest is basically just plugging all of these numbers into your calculator and solving for B. And when you do that, the final answer that you find is let me put it on a new page. The final answer that you find is that the magnetic field required to keep the loop at 30 degrees is 0.024 Teslas. And that's the magnetic field at which the torque due to gravity is balanced by the torque due to the magnetic field, and the loop stays at 30 degrees. That's all.